All right, my name is Mr. Jern, and I'm going to talk to you about mechanisms. This is 1.1 for Project Lead the Way, Principles of Engineering. And we're just going to talk about levers, wheels, and axles, and pulleys for this one. There'll be a part 2 after this. So, first things first, let's talk about simple machines. All right, simple machines, and this is just one of those things you should know, is a mechanism that manipulates the magnitude of force and distance. All right, I'll talk about the implications of that in a second. These 6 simple machines are these. You got your lever, wheel and axle, and your pulley. And these are the ones we're going to talk about in this video. We'll talk about the next one, or these next 2 in the next video. The inclined plane, the wedge, and the screw. Okay, all those 6 simple machines make the foundation for all the mechanisms that we have. So what is the point of these machines? Well, the point of these machines is to get mechanical advantage, MA. And you're going to see, this is like one of the things you're going to see a lot of in this class, mechanical advantage. This is why we do things. We want mechanical advantage. It basically, well, I'll talk through it. Mechanical advantage is the ratio of the magnitude of resistance and effort forces. Okay, so that's the first part of it. In other words, how much effort do you put into something, and how much effort do you get out of it? How much force do you get out of it? How much force do you put into it, and how much force do you get out of it? Okay, you think of a lever, you could put a little bit of force into something and you get a lot of force out of it. Okay, you could lift heavy things with not a lot of force. Why is that? Well, that brings us to our second part of this. It's the ratio of the distances traveled by effort and resistance forces. So if you think of the lever, the part where you have to push, what's called the effort force, is going to move a lot farther than the part that's moving the object, the resistance. So there's a trade-off between force and distance. So if you want something to be easier, you're going to have to travel more distance. And the flip side is true too. If you want to travel less distance, you're going to need to apply more force. So that's the underlying principle behind mechanical advantage. So I'm spending a lot of time on this one because I need you to understand that. Okay, these ratios of the trade-off between force and distance is the underlying like fundamental idea that allows us to manipulate all these things: speed, distance, force, and function. So going ahead with that, we have this inclined plane. And for this inclined plane here, we have a mechanical advantage. This tells us it's a ratio, remember, of 4:1. That's our mechanical advantage. Well, what does that mean? Take a look at this. What do you see? Okay, what's the difference between lifting a box straight up and sliding it up a ramp? Well, if you think about it, think about the magnitude of force, the red arrows. It's going to take a lot more force to lift something straight up than it is going to be to slide it up the ramp. Okay? Now, what's the trade-off? Well, we'll get to that in a second. Because we have a mechanical advantage of 4:1, that tells us that the force, the effort force, the force it's going to take to move this ramp or this block up the ramp is going to be 4 times less than the magnitude of the resistance force. Okay, what do I mean by that? Well, what are we doing? We're lifting. We can either lift this box straight up, like we did on like what's going on the left, or we can use this ramp to lift it also up. Okay, what's the point of a ramp? It's not to like have a good time. It's to raise something up to a height. And so that's what we're doing. So in order to lift this box up, the one on the left takes 4 times the amount of force to lift it up compared to the one on the right going up the ramp. Now, what is the trade-off? Well, the trade-off is the distance. So as you can see, the effort force on the one on the right, the distance, it's going to travel 4 times as far because, well, that's the mechanical advantage. You get to push 4 times with 4 times less force. Okay? That is the essence of mechanical advantage, using the ramp as an example, the inclined plane. Okay? So that brings us to a physics term called work. And if you remember physics, if you've taken it yet, it's a simple concept. Work is just the force applied on an object times the distance that it travels, parallel to the force. That's important. Okay, parallel to the force. So the simple idea is work is just force times distance. Okay, work is force times distance, and this little line right here, that just means parallel. Okay, so if you push this yellow block to the right, then you measure the distance that it moves to the right. All right, so Why is it important that we point out the parallel thing? Well, we're going to get angles and all that involved later. So work is force times distance, parallel to the direction of the force. Okay, so fancy little diagram there. It just shows us the distance that it moved. Now, something to keep in mind is that the way mechanical advantage works is that the work you do, whether you use a mechanical advantage, take advantage of it, you use a machine or not, it's going to be the same, regardless of what happens. Okay, look at this example here. Whoop. I mean, if work is force times distance, well, the one going straight up requires a lot more force, but it doesn't require much distance. And the flip side is the one going up the ramp, up the inclined plane, doesn't require much force, but requires a lot more distance. When you multiply the force times the distance for either block, it's going to be the same amount of work. All right. So that's the nice thing about this is you want to get some work done. You want to move something. You can use mechanical advantage and you're going to do the same amount of work. Now, when we talk about mechanical advantage, 1 is the magic number, all right, because it's a ratio. And if your mechanical advantage is greater than 1, well, that means it takes proportionately less effort force to overcome the resistance, but it's going to take more distance to overcome that resistance force. If the mechanical advantage is less than 1, then it's going to take a greater effort force and it's going to require less distance. Okay. Keep in mind that it's a ratio and mechanical advantage can never be less than or equal to 0. Okay. If it's 1, by the way, what does it mean if it's 1? Well, that means you don't have any mechanical advantage and you're just getting a 1-to-1 ratio. So now we get into some calculations. And what's going to happen here is we're talking about ideal mechanical advantage. This is theory, okay? Ideal means this is like if all the math worked out perfectly and we ignored friction. This is what it would be like. So friction is not taken into consideration. You can eliminate, you can't eliminate friction, but you can reduce friction to get closer to your ideal mechanical advantage. Okay, now ideal mechanical advantage is just the distance, the ratio of the distance traveled by the effort and resistance forces. So this is an equation that will be on the equation sheet for any tests. You won't have to memorize it, but you are going to want to be familiar with how to use it. So the ideal mechanical advantage is DEER, the distance traveled by the effort force divided by the distance traveled by the resistance force. Okay, IMA is DE over DR, DE over DR. It kind of rolls off the tongue if you say it enough times. DE over DR, he says with ease. So let me give you an example in a minute, but that's ideal mechanical advantage. Then you have actual mechanical advantage. What is the mechanical advantage that you're going to get in the real world where frictional losses are taken into consideration? Now, going back a slide, the ideal mechanical advantage is all just pure math. Okay, you make some measurements, you don't actually try anything, and you get your ideal mechanical advantage. Actual mechanical advantage is, it says inquiry based. That means that you actually are going to take measurements of force and everything. All right, so frictional losses are just going to be built in. Okay, and now because actual mechanical advantage is just the ratio of the force magnitudes. So what is the actual amount of force of the resistance divided by the actual magnitude of the force of the effort? Okay. So there's two different types of mechanical advantage, or rather it's the same mechanical advantage. It's just one is more theory based and one is more reality based. Okay, and both are important. So in the real world, mechanical advantage, can you think of a machine that has a mechanical advantage of greater than 1? Maybe a windmill? Okay. Can you think of a machine that has a mechanical advantage of less than 1? So if a machine has a mechanical advantage of greater than 1, well, what does that mean? What if it has a mechanical advantage of less than 1? Can you think of anything there? Okay, maybe some resistance equipment. Okay, you want to travel less distance, so you have to apply more force, right? All right, so that's mechanical advantage. Let's talk about some different machines. Okay, but there were 6 of them, remember, and the lever is one of them. A lever, you know what a lever is. It's a rigid bar used to exert a pressure. Now this is the definition of a lever. You can memorize it if you want to, but I think you know what a lever is. The important thing is understanding that you have a pressure at one point, you have a pressure force at another point, and you have this fulcrum in the middle, or maybe not in the middle, but you have this fulcrum, which is basically where it's tilting, it's rotating on. Okay, so the fulcrum is represented by, I mean, like this top one here is your typical seesaw lever. You know, there's the fulcrum right in the middle, and you got your effort force and your resistance forces on either side. Okay, then you got 2 other kinds of levers, which you may have learned about a few years ago. So there's 3 kinds of levers. 3 kinds of levers. The first class lever, just think of your typical seesaw lever. The fulcrum is located between the effort and the resistance forces. Okay, that's the definition of it. The effort and resistance are in the same direction. So you push down on one side and the resistance is trying to push down on the other side. Okay. This one, you can actually adjust the fulcrum and you can get your mechanical advantage to be greater or less than 1. You could change it up depending on what you're trying to go for here. So look at the different kinds of first class levers, and you can see if you slide the fulcrum over one side, you're going to get a mechanical advantage of less than 1, and if you slide it to the other side, you're going to get a mechanical advantage of greater than 1 because you had to apply, you know, less force to lift up a heavy object. So the next kind of lever is a second class lever, where the fulcrum is located at one end of the lever. Okay, just think of this is your wheelbarrow example. All right, where your resistance force is located between the fulcrum and the effort force. So on a wheelbarrow, you'll be lifting up on one end, and the weight or the resistance is right in the middle, and the fulcrum or the wheel is at the other end. Okay, it always has a mechanical advantage of greater than 1. So in other words, you have to lift this end up greater distance than the resistance force is being lifted up, and the trade-off is you don't have to lift with as much force. So it's always going to have mechanical advantage of greater than 1. Third class lever, think of tweezers. There's a couple other things, but tweezers is the one I always think of, where the fulcrum is located at one end of the lever. Okay, but in this case, the effort force is located between the fulcrum and the resistance. So this is why I think of tweezers. Here's the tweezer end where like they're connected, and you push on the middle of the tweezer. On one end, there's another side coming together up here. And then the tweezers are coming together over here. Okay, so here's the resistance force, here's your effort force, you push here, here's the fulcrum where it rotates around. These always have a mechanical energy or mechanical advantage of less than 1 because you have to go much greater distance, or I'm sorry, you have to go with much greater force, but you have to travel less distance than the resistance. So just a term, we're going to come back to this a lot in later classes, weeks, but moment is probably a brand new word for you. So just take a moment, haha, that was unintentional. Just take a second and just absorb this, pause it if you need to. Moment is basically, well, here, it's the turning effect of a force around a point equal to the magnitude of the force times the perpendicular distance from the point to the line of the action from the force. All right, well, that's a lot. Just think of it this way. Think of it mathematically. That might help a lot. Moment, capital M, is equal to the distance times the applied force, times the force. It could be applied or it could be resistance, doesn't matter. Okay, so we'll get back to that in a second. So you have a moment over here. You take the distance from the fulcrum to the, I believe this was the effort force, and you multiply that times the force. That'll be the moment here. Over here, you take the distance times the resistance force, we'll call it, and that'll be the moment on this side. Now, if these are balanced, the moments will be canceled out and they'll be equal, but we'll get to all that later. So moment, just for now, it's a vocabulary term with an equation. Okay. Torque, just think of torque as force in a circle. All right, it's a force that produces or tends to produce a rotational rotation or torsion. All right, it's not a, listen, force in the physics term is a vector, it's a straight line. Okay, torque is a circular version of that, and there's reasons we separate those two as different terms. So when we talk about our lever, and here's where we're going to get into moment a little bit. What is the effort moment acting on this lever? So we have the effort now over here, over here, and it's 15 pounds, and the distance from the fulcrum to the effort force is 5.5 inches. Well, moment is distance times force. So you're like, hey, Mr. Jern, why aren't we using newtons and centimeters? Well, this is engineering. We use these. This is the stuff we use in engineering, and it's okay. Get used to using both, right? So effort moment is just the distance times the force. So we take 5.5 times 15. And then when you multiply that, you get 82.5 foot-pounds of moment, okay? Whoop. And that's it. That's the moment. You're like, what are these units? That's the unit of moment. So welcome to the club of engineering. You know what a moment is now. Why is that important? Well, because we'll get there in a minute. But yeah, the effort moment is 82.5 inch-pounds, okay? So here's the deal. I mentioned this earlier. When the sum of all the moments on a lever equals 0, that means that lever is in rotational equilibrium. They're balanced, okay? When the sum of all the moments is equal to 0, that means there's no movement, or it's in equilibrium. It could be rotating with, just constant velocity, but it's balanced out, okay? Rotational equilibrium is this. It's when all the clockwise moments equals the sum of all the counterclockwise moments around a pivot point. So think of a seesaw where you're perfectly balanced, or think of a bicycle tire that is just spinning perfectly and not slowing down, all right, because it's just at a constant speed because there's no acceleration. So why is that important? Well, check this out. What do we know? We could calculate the unknown distance. If we know that we're going to push with 15 pounds over here, 5.5 inches away, and we know we want to lift a 36 2/3 pounds object over here, how far away does that need to be? Well, if they're in equilibrium, then we set them equal to each other. So the effort moment is counterclockwise against the clock, and the resistance moment is clockwise, and they're equal to each other. So what's the effort moment? It is the counterclockwise moment, where we take the force times the distance, 15 times 5.5, so it's down here, and we're going to set that equal to the clockwise moment. Moment is force times distance. So the force is 36 2/3 pounds, and the distance is whatever our resistance distance is going to be. That's our unknown. So now we have something to solve for. So what do we got to do? Well, we're going to simplify the left-hand side of the equation. We multiply that. We got area 82.5 like before, inch-pounds. And now we're going to have to divide both sides by 36.66 pounds. And when we do that, well, the pounds are going to cancel out, and we're left with 2.25 inches. So now we know. We leave that at 2.25 inches away. And that's very useful. Okay. Definitely something you might need to rewind and watch that again to take that in, or pause it and think about it a little bit. All right. Because it's brand new stuff to you. And in retrospect, it's not difficult, but it's new, and it's probably difficult when it's new. All right. So the lever IMA, the ideal mechanical advantage, how do we figure that out? Well, just like any IMA, we take our effort distance divided by our resistance distance. All right. Now the circumference around any circle is just going to be 2 pi r, right? So that is so we translate that into our effort distance is going to be 2 times pi times r, and r is the effort arm length. So what is the radius? That's going to be however long this arm is. So if you think about it, this is going to spin around in a circle if we just let it spin. So we could treat it like it's a circle. So the resistance distance is going to be 2 pi r to 2 pi times the distance here, okay? So when we take those, we could figure out the IMA is going to be this equation right here, and guess what? Whenever you got that, they could just cancel out, and basically the lever IMA, the lever ideal mechanical advantage, is going to be whatever the length of the effort arm length is divided by the length of the resistance arm length. That's it, okay? Another thing you could you could remember or write down it'll be on the equation sheet. So you don't have to remember all this, but you got to be able to use that. So make sure you know what all these things are. What about the lever AMA, the actual mechanical advantage, when friction and air resistance and all that stuff is involved? What's going on there? Well, the AMA, just like any AMA, is the resistance force divided by the effort force. So what's our resistance force? Well, think about it. What is the AMA of the lever above? What's our resistance force? What is our effort force? Divide them. That's it. So we take our 32 pounds divided by our 16 pounds. Pounds cancels out. We are left with a ratio of 2 to 1. So that's our actual mechanical advantage. Okay. So you remember the IMA? Well, it's just the effort distance divided by the resistance distance. So let's do that too. We take that, nice easy calculation. It just cancel out. We're left with a ratio. And our IMA if there was no friction and nothing like that involved, our mechanical advantage would be 2.44 to 1. But with friction and all that junk involved, it turns out that our actual mechanical advantage is only 2 to 1. Why? Why would they be different? Why is the actual mechanical advantage different than the ideal mechanical advantage, a calculated mechanical advantage? And I've been dropping hints like nothing. And so what is it? Well, it has to do with friction. Okay, friction doesn't play a role in our ideal calculations. There's not really a way to calculate that. We try to reduce it as much as possible. So it is in our AMA though. And that's what brings us to efficiency. All right, efficiency is basically we lose energy every time that there's friction involved. Okay, whenever there's friction, it takes energy to overcome that friction. So we're interested in useful energy output. So what we do to figure out the efficiency is we take our AMA divided by our IMA and multiply it by 100. It's going to give us our percentage efficiency. So in the previous example, the AMA was 2 to 1, the IMA was 2.44 to 1. So we divide those out, we multiply by 100, and it turns out that that lever is 82% efficient, which is amazingly efficient. Okay, if you think about it, there's not a whole lot of friction involved in a lever. You might be like, that's 82%. That's a B, Mr. Jern. Yeah, I know. That's just, that's welcome to the real world, right? So keep in mind that no machine is 100% efficient. It's not possible. Not possible. All right, that's the lever. Wheel and axle. We're not going to spend nearly as much time on the wheel and axle because a wheel and an axle. A wheel is just a lever arm fixed to a shaft. So we already learned about the lever. Think about it. Look at this little diagram here. What's going on here? Well, it's a lever being spun around. It's a multi-dimensional lever. It's just been sort of extruded out into like a little loop there. So you could think of it as a lever. In fact, we're going to think of it as a lever that spins around like that. Basically, the wheel and the axle. So you got a wheel, and here's where it kind of comes into play. The calculations. This is why it's a little bit different. Is because you have this axle that's attached to it. That's a separate diameter right there. You have to keep in mind. All right, you have two diameters to keep in mind to work with here. You have the diameter of the wheel, and you have the diameter of the axle. And so those two are going to play together, and we're going to get mechanical advantage out of that. So now the important thing to know is which one is applying the effort and which one is applying the resistance. In a case of a wheel like this, usually when you're accelerating or positively accelerating, speeding up, the axle is applying the force to the wheel, okay? And so it'll slow down. Like there's other ways where it's the reverse. In fact, that's kind of like a question. Can you think of an example of a wheel driving an axle where you actually turn the bigger parts to make the smaller part turn? Here's some examples. A steering wheel. You're turning a big old wheel, makes it nice and easy to turn that little tiny shaft in the middle. Okay, same thing with any dial or valve turny thingy. Oh man, I totally slipped my mind if that has a name separate from valve. A valve. Oh well, look it up on the internet, right? So how do we do the calculations? Because that's what this is all about. The wheel and axle. IMA, the ideal mechanical advantage, just like before, effort distance divided by resistance distance, okay? But you do have to know which is the effort, which is the resistance. So again, just like our example before, we got our circumference. It would just keep spinning if we didn't oppose it. So we deal with circumference, and in our case, the effort distance is just going to be pi times the diameter of the effort. Okay. In our case, we don't know is the diameter of the wheel or is it the axle. We haven't decided. We haven't determined that at this point. The resistance distance will be pi times the diameter of the resistance, whether it's the axle or the wheel. We haven't determined that at this point. So what's going to happen is when you take those and you divide them by each other, the pi is going to cancel out, and you just, again, take the effort diameter divided by the resistance diameter. So whichever is the effort, take the diameter divided by whatever the resistance diameter is. So if in this case the axle is driving the wheel, what would the IMA be? So the axle is 6 inches in diameter. The wheel is 20 inches in diameter. Okay, so the axle is driving the wheel. Well, the effort diameter is the axle, so you take that, 6 inches divided by 20 inches, inches cancels out, we're left with a 0.3, which is a 0.3 to 1 ratio. Kind of ugly, so we multiply everything by 10, and we get a 3 to 10 ratio. That's the IMA. Okay. What if the wheel is driving the axle? Well, you just take the inverse of that. You take the 20 divided by the 6 inches, and you get a 3.33 to 1 ratio for the IMA. What about AMA? All right, well, it's the same thing. In this case, you have to have actual measurements. So like the other one, you could take distance measurements, I should say. But in this case, you actually had to do actual tests to see, well, how much force does it take to do this? How much force does it take to turn that? So right now here, it takes 70 pounds of effort force to turn a 200-pound resistance. Okay. In fact, I think that's what's going on the other way around. Actually, I haven't decided. Okay. It's the wheel driving the axle. Yeah. So the wheel is driving the axle. So you push with 70 pounds of force and you get 200 pounds of, you're able to overcome 200 pounds of resistance on the axle. Well, the AMA is just the force resistance divided by the force of effort. So 200 pounds divided by 70 pounds, the pounds cancels out, and you're left with this ratio here, 2.86 to 1. What's the efficiency of the wheel and axle assembly? Well, you gotta go back a little bit, and remember, efficiency is just the AMA divided by the IMA. So our AMA, 2.86, divided by the IMA from the previous slide, multiply that by 100. And so you get an 85.9% efficiency. Okay. Once again, the actual math is division and multiplication in a lot of cases, but you got to learn, you're going to have to get used to applying this math. Okay. Our last simple machine of this video, a pulley. It's a lever consisting of a wheel. So, hey, we've seen all this before, right? So a pulley is just a lever consisting of a wheel with a groove in its rim that's used to change the direction and magnitude of a force exerted by a rope or a cable. Now, you know what a pulley is. You can picture it, but here's a definition of one. How do you figure out the IMA? Okay, this is where it gets a little bit different. You have to understand that we got two different types of pulleys. We got fixed pulleys where it ends up being a first-class lever with an IMA of 1. All right, all it does is change the direction of the force. So you pull down with 10 pounds of force on a fixed simple pulley. That means that you're able to lift up 10 pounds of force. So 10 pounds down means 10 pounds up. But a movable pulley is going to give you some mechanical advantage, all right? Because this ends up being a second-class lever. So go back and see if you can figure out how this ends up being a first-class lever. Look at the little diagram. You can see how it works. Okay, look at this diagram over here. Go back and see what a second-class lever is if you forget. Okay, see why this is a second-class lever. So now you get an IMA of 2, okay? And the force direction stays constant. So if you lift up with 5 pounds of force over here, the support structure is lifting also up with 5 pounds of force. And so you're able to lift up this 10 pounds of force that's pulling downward. So let's extrapolate that a little bit. So you've got this combination pulley. Well, look it looks super complicated. How much effort is it going to take to lift up this 600-pound motorcycle? Well, we're going to figure that out, and it's really simple. Okay, if you have a single rope or a cable threaded through multiple pulleys in a system of pulleys, so a single unbroken rope, you can follow it from beginning to end, and all you got to do is count the number of strands opposing the force of the load. Okay, the number of strands opposing the force of the load. So you don't count the one you're pulling on. So how many strands are there opposing the load? 1, 2, 3, 4. So the IMA, the ideal mechanical advantage before friction and all that stuff's involved, is going to be a 4-to-1 ratio. Okay, so you could start to do quick analysis in your head. How much is going to be required to lift this up? So there you go. So you don't count the one you're pulling on, and then you just count the strands that are opposing load if it's a single rope. So actually, I don't know why I didn't have that up on here. So yeah, it'll be 150 pounds to pull this 600-pound motorcycle up. So can you lift it up? Well, if you weigh 150 pounds or more, you can lift up this motorcycle. Okay, if you weigh less than 150 pounds, you're not going to be able to budget. Okay, so compound machines, you could put a little pause button there if you want to just digest stuff for a second. But compound machines here are when you take one simple machine used after another, all right? And when you do that, the mechanical advantages just simply multiply. So you have a pulley here, you have a lever here. What's going to be the total IMA, total ideal mechanical advantage? Well, you just multiply the IMA of the pulley times the IMA of the lever. That's it. So the number of strands for the pulley, there's 2 strands, and the effort distance divided by the distance resistance distance of the lever. Okay, and it turns out you multiply those two together, and in this case you just get the mechanical advantage of 6. Now when it comes with pulleys and combinations, we're getting to the end here. When it comes to pulleys and combination, when you have separate ropes, how do you do that? Well, it's basically the same thing as before. It's a compound machine. Okay, so what you do is you find the mechanical advantage of each pulley and you multiply them together. So the total IMA is just multiply the IMA of each pulley. All right, so this is it's just 2 times 2 times 2. All right, so what's the AMA of a pulley system here? Well, the AMA is still going to be the resistance force divided by the effort force. So in this case, what's our resistance force? 230 or 800? What's the resistance force? 800. So take the resistance force divided by the effort force, and that's going to give you your actual mechanical advantage because pounds cancels off and you're left with a ratio once again. What's the efficiency of this pulley system? Well, the actual mechanical advantage is 3.48 to 1, and this is a compound pulley, so we just count the strands that are opposing to the load. 1, 2, 3, 4 is going to be our mechanical advantage here. So we take our AMA divided by our IMA, our 3.48 divided by our 4, multiplied by 100, and our efficiency is 87%. Not bad. Okay, there's a common misconception that angles don't matter. Pulling with 40 pounds here, it does matter, because you got to understand that this IMA definitely only comes into play if the strands are opposite or parallel to the resistance force. So think about this: you're pulling straight up with 40 and 40. The weight of this is pulling straight down with 80. So we got our IMA of 2. In this case, the things are at an angle. So why do we have to pull with 46 and 46? Why can't we just pull with 40? Well, because the effort force that you require is actually you need to pull straight up. And so since you're pulling up and to the side a little bit, some of that effort is off to the side. And if you, and this will require trigonometry, which I will show you how to do, not now. Okay. Another common misconception is you just count the effort strands if it pulls up. Well, sometimes. Okay. It's the pulley IMA is the number of strands opposite the load, opposing the load. So if it opposes the load, you count it. All right. So in this case, we have an IMA of 2. All right, because it's not pulling upward in this case. This pulley is pulling it downward. Okay. The other examples I showed you were pulling it upward, not this case. So the effort force in this case, the support structure is pulling it downward. The effort force is pulling it downward. That is opposite of the resistance, which is trying to pull back up for some reason. I don't know what's going on here, but you could use your imagination. So, yep, It just has to be opposite the load. So that is a mechanical advantage and 3 of simple machines. There's another video going to be coming soon. It's just part 2, and that'll be the other 3 machines. So let me know if you have any questions.